in the vastness of the cosmos. Few things inspire as much awe and terror as a black hole. They are symbols of the absolute extreme, a place where space and time fold in on themselves, where the familiar laws of physics seem to cease. A black hole is a region of space so dense that its gravitational pull is strong enough to trap even light. To us, it's an endless abyss, a point of no return where everything that falls in vanishes forever. But what makes black holes so haunting isn't just their power, but their absolute silence. No light, no signals, nothing can ever leave. For decades, science believed this was the final frontier. A black hole consumes all, and nothing, not even information, can escape. But in 1974, the physicist Stephen Hawking stunned the world with a seemingly paradoxical question: do black holes explode? That question alone was enough to shatter every definition humanity held dear.
All black holes evaporate. Its evaporation is its energy field is so intense that matter spontaneously spawns in that energy field. And in so doing, the black hole loses mass.
Gotcha.
And so the act of its losing mass is because it's sending matter and energy
Out.
beyond its event horizon.
Hawking's discovery didn't just challenge the classical definition of a black hole. It ignited one of the greatest revolutions in modern physics. For the first time, it connected three pillars of science that seemed irreconcilable: general relativity, quantum mechanics, and thermodynamics. If black holes truly emit radiation, they are no longer absolute voids, but dynamic objects with temperature, entropy, and a life cycle. And that forces us to ask, is it still true that nothing can escape a black hole? Before the 1970s, the scientific consensus was clear: a black hole was the absolute end for matter. Once anything crossed its event horizon, nothing, not even light, could get out. According to Einstein's theory of general relativity, their gravity is so immense that all paths of light are bent back on themselves, making a black hole a perfect dark abyss where time and space are locked away. But in 1972, a young physicist named Jacob Bekenstein noticed something strange while studying them. He realized that the surface area of a black hole's event horizon could never decrease, only increase. This was identical to the law of entropy in thermodynamics, which states that the total disorder of an isolated system can never go down. Bekenstein proposed a bold idea: black holes have entropy, and its value is proportional to their surface area. He argued that information about what falls into a black hole isn't lost forever but is encoded on its surface, as if the event horizon were a two-dimensional hard drive storing all the data it had consumed. However, if a black hole has entropy, then, according to the laws of thermodynamics, it must have a temperature. And if it has a temperature, it must emit thermal radiation. This directly contradicted the classical definition: a black hole cannot emit anything. Stephen Hawking initially rejected the idea, but he decided to test it with his own mathematics. Using quantum field theory in curved spacetime, Hawking analyzed energy fluctuations near the event horizon and was shocked to discover that black holes do, in fact, radiate. This radiation is incredibly faint, but it has the exact thermal spectrum of a blackbody radiator. The energy for this radiation comes directly from the black hole's mass. So, over time, it loses mass and shrinks. The smaller it gets, the stronger the radiation becomes. Finally, in a brilliant flash of energy, the black hole explodes and vanishes completely. This left a burning question: if nothing can escape a black hole, how does this radiation get out? The answer lies in the quantum nature of the vacuum, a place where, even in absolute emptiness, strange energy fluctuations constantly occur, a phenomenon Hawking would explain next. To understand what Stephen Hawking discovered, we must start with the foundation of modern physics. Everything in the universe isn't truly a particle, but rather a vibration in an energy field. Imagine the entire universe as a vast ocean. When the wind blows, ripples form on the surface. In quantum physics, every type of particle, electrons, photons, protons, is just a different kind of ripple on that ocean. These vibrations create everything we see, from light and sound to matter and gravity itself. Physicists call these quantum fields. There are dozens of them, all overlapping and filling all of space. when nothing is happening. A field is quiet, like an unplucked guitar string, but when energy is introduced, a collision, a light source, an electric charge, that string vibrates, creating the note we perceive as a particle. Therefore, in the so-called vacuum, there is no truly empty space. Space is teeming with fields in a state of faint vibration, constantly fluctuating in and out of existence. It is within these subtle vibrations that the universe creates what Hawking saw. Energy can emerge from what appears to be absolute nothingness. And when a black hole enters the picture, things get even more interesting. Its colossal mass warps spacetime, distorting the quantum fields around it. It's like placing your finger on a vibrating guitar string. The melody instantly changes. At the boundary of the black hole, the quantum fields are no longer in balance. Some of their energy begins to leak outward, while some is pulled inward. It is here, at this boundary, the event horizon, that the strangest quantum effects in the universe begin to unfold. And it leads to the most paradoxical phenomenon in all of physics: particles can be born from empty space. According to the Heisenberg uncertainty principle, on the smallest scales, it's impossible to simultaneously know a particle's exact position and momentum, or the precise energy and duration of a process. This means the vacuum is never truly still. It constantly produces pairs of virtual particles and antiparticles, which exist for a fleeting moment before meeting and annihilating each other. This phenomenon is real, though invisible to the naked eye. One piece of experimental proof is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, they are pushed together by a pressure difference in the quantum fluctuations between them and the space outside. This proves that the vacuum actually has energy, pressure, and is never quiet. Near a black hole's event horizon, these virtual particle pairs are torn apart by the extreme gravity. Sometimes, one particle is pulled in, while its partner escapes. Normally, they would annihilate each other. But separated by the event horizon, the escaping particle loses its partner and becomes a real particle, flying out into space. The particle that falls in is considered to have negative energy because, to a distant observer, it reduces the system's total energy, causing the black hole to lose mass. The escaping particle is Hawking radiation. This process doesn't violate the conservation of energy. It simply shows that energy and gravity can be exchanged across the event horizon. For every particle that escapes, the black hole pays the universe back with a tiny bit of its own mass. It's important to note this is just a visualization. In reality, Hawking's math didn't describe individual particles, but calculated how quantum fields behave in curved spacetime. In this understanding, the vacuum is observer-dependent. A person free-falling into a black hole would feel nothing special, while a stationary observer far away would see the area around the event horizon glowing hot with radiation. This is analogous to the Unruh effect, where an accelerating observer also perceives the vacuum as a warm bath of energetic particles. With this foundation, we can understand that Hawking radiation doesn't come from inside the black hole, but from the region of space just outside it. The interaction between quantum fields and the curved geometry of spacetime creates the phenomenon. Think of the black hole as a cosmic bank. Every time a particle is emitted, the bank loses an equivalent amount of energy. And slowly, its mass dwindles. Hawking radiation is incredibly weak. A black hole with the mass of our sun would have a temperature of only 60 nanokelvins, tens of millions of times colder than the 2.7 Kelvin cosmic microwave background. This means it's actually colder than the space around it. In fact, astronomical black holes are absorbing energy from the cosmic background much faster than they are radiating it away. Only primordial black holes, much smaller ones that could have formed just after the Big Bang, would be hot enough to emit significant radiation. In the final stages of their evaporation, these tiny black holes could reach temperatures of billions of Kelvin, erupting in a powerful burst of gamma rays before disappearing. Astronomers are actively searching for signs of such explosions, as finding one would be the first direct proof of Hawking's theory. But Hawking radiation is more than just a mechanism for energy loss. It's a window into the world of quantum gravity, where two seemingly separate fields of physics finally meet. Yet, it also opened up a new mystery if a black hole truly evaporates. Where does the information about everything that fell into it go? While we can't yet directly observe Hawking radiation from a real black hole, scientists have devised clever ways to simulate the effect in labs. At the Technion Institute of Technology in Israel, Jeff Steinhauer's research team created a sonic black hole in a stream of super-chilled gas by making the gas flow faster than the speed of sound at a certain point. They created an event horizon where sound waves couldn't travel back out. After thousands of measurements, they detected acoustic fluctuations with a thermal spectrum that almost perfectly matched the predictions for Hawking radiation. In optics, scientists created optical black holes using powerful laser pulses in nonlinear materials. A rapidly changing refractive index in the material acted as an event horizon for photons. And at that boundary, they observed the emission of infrared photons, an optical equivalent of Hawking radiation. While these models lack real gravity, they show that Hawking's mathematics holds true across different physical systems. On a cosmic scale, discoveries from LIGO and Virgo have reinforced the theory's foundation. By analyzing the gravitational wave signal from the GW150914 event, physicists confirmed that the surface area of the event horizon did not decrease after two black holes merged, just as Hawking had predicted. This was critical proof that the area law, the basis of black hole thermodynamics, is correct. However, Hawking's theory gave rise to the black hole information paradox, one of the biggest questions in modern physics. If Hawking radiation is completely random and carries no information, then, when a black hole evaporates completely, all the information about the matter that created it is lost forever. This violates a fundamental principle of quantum mechanics. Information can never be destroyed. This created two opposing camps. One, led by Hawking, believed that information was truly lost, meaning quantum mechanics was incomplete. The other, featuring physicists like Leonard Susskind and Gerard 't Hooft, insisted that information must be preserved. We just didn't understand how it got out. The debate raged for nearly 30 years until, in 2004, Hawking famously conceded he was wrong. He came to believe that information is not lost, but is slowly released in the radiation through very subtle quantum mechanisms. Today, many researchers propose that black holes may have quantum hair, tiny imprints in their surrounding gravitational field that store and transmit information. If true, Hawking radiation is not perfectly thermal, but contains faint traces of what fell in. This is seen as a major step toward resolving the information paradox and a key to a future theory of quantum gravity. But one thing is certain: black holes are no longer silent. Static abysses. They have a temperature, entropy, a life cycle, and they will, eventually, die. In the far future of the universe, when all the stars have burned out and the galaxies have grown cold, the slow evaporation of black holes will be the last acts of energy, the final faint whispers in a fading cosmos. What Stephen Hawking discovered changed how we see the universe. We went from believing there were places of no escape to realizing that even absolute darkness can leak light no matter how faint the glimmer. But the story of the black hole is far from over. New research on quantum hair, the holographic principle, and quantum gravity continues to peel back deeper layers of mystery where information, energy, and space-time itself become one. If you want to keep exploring the final frontiers of the universe where physics, philosophy, and imagination meet, subscribe to our channel, hit the notification bell, and leave a comment about what topic you want to dive into next, because perhaps the answers to the universe's greatest questions are beginning to emerge from the very place where nothing was ever supposed to escape.